So good afternoon. So welcome to what I hope is a sporadic, occasional series of talks from our industrial collaborators. And today we're very pleased to welcome Tony Grichnik to come and talk to us, who is the global technology leader at Caterpillar in the US. Caterpillar is the world's leading manufacturer of heavy construction plant, and Tony, though he has a different sort of title, he's obviously their innovation director. To bring people together with new ideas around problems to develop diverse solutions. And I think we're all in that. Come on.
Come on in.
That's all right. Come on in.
Hesitate, it's the wrong place.
That's all right.
And I think we're all in that business in one way or another. His educational background is a Bachelor of Science in Mechanical Engineering, so very well trained at Valparaiso University. And he also holds a Christ College Honours in Humanities, Arts and Theology, so liberal arts. He completed the New Entrepreneurs Programme at the University of Chicago, and more recently, the Supply Chain Executives Programme at MIT Centre for Transportation and Logistics. He's currently Caterpillar's visiting scientist at Bradley University in their Intelligent Systems Laboratory and teaches on their Master's Programme in Computer Science. In his professional life and at Caterpillar, he has produced over 40 US patents in a range of fields: manufacturing quality, supply chain modelling, signal analysis, pattern recognition, medical diagnostic and virtual sensing, which are actually all things we are interested in. So, and these technologies are used to develop and produce nearly all of Caterpillar's current engine and transmission systems, as well as design their global supply chain. Several of the patents support Caterpillar's healthy, balanced employee wellness program as well. So it's more a holistic look at Caterpillar as a whole. And outside Caterpillar, he's one of the founders of Smart Energy Limited, which is a company developing wind energy for home heating and cogeneration. So the collaboration between Caterpillar and Brunel started in 2011 in the area of global supply chain optimisation. And since then, we got involved in an award-winning gemstone technology, which is the generation and evaluation of manufacturing, supply and transportation optimization networks, which Tony's going to talk about, which has been developed collaboratively with Tatiana, leading the Brunel team, and with Caterpillar, and has been successfully implemented in Caterpillar right the way across their business. So a very successful implementation of the impact story. And so, Tony, thank you.
Thank you.
Visitors today are going to talk about supply, network modelling, and optimization.
Fantastic. Thank you. Thank you all for coming this afternoon. So yes, I'm going to talk a little bit about supply network modeling and optimization. We'll do that in a number of different ways. Some will be kind of more descriptive, and some things we'll actually do some demonstrations of how our tools work and how we apply them to real problems. But I'd like to start with kind of a strange observation. And that's that actually we're really not interested in the modeling and optimization of our global supply network, which is kind of weird because that's what I'm here to talk about. But what I mean by that is this: there's a big difference between being interested in something and being committed to something. If you're interested in something, you do it when it's convenient. When you're committed to something, you accept no excuses, only results. So our group is extremely committed to modeling and optimization. You'll find a number of other companies that kind of dabble in this space. We don't. We take it extremely seriously, and we'll show you why we take it seriously as we go through the presentation. So I'll break that into 4 pieces this afternoon. I always like to start with sort of fundamental business questions. So if we're going to have some process or mathematical thing, what's the questions it's trying to answer for the enterprise? Then I'll talk a little bit about tools, and I'll actually demonstrate those and how we use them by actually using some of them here in the room. I figured it's appropriate, since I'm here in the UK, to talk a little bit about what happens after the Brexit event and our thoughts on where that might be going. We'll share that as sort of one man's opinion, but I think you'll find the discussion very interesting. And then we'll talk about integration and Outlook, which is where do we go from here? We've come a long way, but we're not done yet. And there's a lot of new things that we still need to develop. Sound good so far? Fantastic. Well, let's start with fundamental business questions. So fundamental business question really comes down to what should we make, where, when, how many, how should we transport it to minimize the environmental impact and maximize the enterprise profitability over time. Now, although it's only one question, there's obviously a lot of moving parts to that. So let's break it down into pieces. So when we talk about what we should make or buy, we're really starting to talk about the recipe. So what are the components that go into this product, and where do they come from? Which components should we produce internally, and which ones should we buy from an outside supplier? So Caterpillar, in case you're not familiar with our enterprise, we like to say, the full-size sandbox toys. We're also the largest manufacturer of generator sets in our range. But in particular, we're vertically integrated. We make most of our own engines, we make most of our own transmissions, we make most of our own hydraulics. A lot of the components are things that we can source from our own internal capabilities, but we don't always do that. Sometimes it's to our advantage to use others. So we try to sort that out using these kinds of models. If we have multiple choice, what makes the most sense in the context of this product versus the context of the whole enterprise? We want to always think with that enterprise point of view. What may make sense to a single product or a single market might actually not make sense when we think about the entire enterprise and the pull on the supply base. And last piece is taxes and tariffs. How do the decisions we make affect the taxes and tariffs that our customers get exposed to? Now, this is a huge issue for Caterpillar. So to illustrate that, we created this heat map. So the darker red the color you see on the map, the higher the worst case tariff on our products. Now, tariffs are a really, really big topic for us. If you were to ask me, Gemstone program has been going on for 7 years. And if you were to ask me 4 or 5 years ago, how fast do tariffs change? I would say not very fast. You could think of the tariffs as a giant matrix, 141 source countries to 141 destination countries. In a typical year, 4 or 5 years ago, we might see 3 or 4 columns or rows change values. So a handful or a small number of countries might change their taxes relative to another country. In the last 36 months, 41 out of 141 have changed their taxes relative to each other. Prior to the change, the average tax on our machines was 4% of sales price. Now the average is 40% of sales price. In some areas of the world, the tax is actually 100%. So for every dollar you want to spend with Caterpillar, you have to spend $1 with the government. So understanding where these boundaries are is really important. So for example, you'll notice that Mexico is colored red in this diagram. And when I give this presentation in North America, people are usually kind of surprised by that. In North America, we have something called the North America Free Trade Agreement, or NAFTA. Now, under NAFTA, if I make the product in North America and I sell it into Mexico, the tariff is 0. And that's true. But what most people don't realize is that it's not 0 coming from other countries. So if I made that same product here in the UK and shipped it to Mexico, it would be subject to a 20% tax, 25% in Japan, 30% in China. So understanding the relationship of the taxes from source to destination is really important. It's one of the powerful variables in the system. Now, when we talk about from where, we begin talking about geography. So in this case, where are the sources? Where are the assembly sites? Where are our dealers? Where are our customers? Understanding that geography is important because the geography dictates time. What are their capacities and their capabilities? Not all suppliers are created equal. Not all Caterpillar plants are the same size. So how much can I get from one source or from one supply versus how much I can get from another one? How do these locations affect in-transit inventory cost and the cycle and safety stock costs necessary to meet a certain response time? So when you think about a supply network, it's really very much about position and time. So when a customer wants a product at a faster and faster rate, ultimately I run into a hard physical limit. Trucks only move so fast. Trains only move so fast. Ships, which move our products, only move so fast, and so fast is not very fast. So we have to eventually start putting inventory in the system closer to the customers. That inventory isn't free, so therefore time is money, right? Time costs us money. And are there other sources we can draw on from the rest of the global supply network? A big chunk of what we do has to do with visualization. So it's one thing to calculate the answer to this big complicated math problem, but it's another thing to explain the answer to a decision maker to get them to take action. So one of the tools we use is Google Earth. And I'll actually use this in the demonstration, so I won't spend a lot of time on it here on this slide. Suffice to say that the arcs are transportation lanes. The thicker the arc, the more volume is moving on that transportation lane. The bars or pins that you see sticking out of the earth, those are inventory positions. Those inventory positions are the result of the promise we made to fill the customer's order in a certain amount of time, and the intersection of that with the supply network, where sources of supply are, and how fast transit can be done. When and how many gets, again, to the time question. How does demand seasonality affect the design of the network? And where does that drive the customers and dealers? Which customers and dealers drive that seasonality characteristic? So Caterpillar products have a huge range. Our least expensive product has a sales price around 20,000 US dollars. Our most expensive product is 20 million US dollars. So the expectations of customers are very different when you have that many orders of magnitude between your least expensive product and your most expensive product. In this case, seasonality often is reflected in that. So some products, particularly the high capital cost products in the millions of dollars, tend to be aseasonal. We'll sell about the same number all year round. On the other hand, some products are hyper-seasonal. Our most seasonal product in the enterprise will sell about 90% of its annual volume in only 6 weeks of the year. So the network that serves that hyper-seasonal product is very different than the one that serves an aseasonal product. How does the seasonality impact capacity utilization and inventory planning? You can imagine that if you have a flat demand signal that's relatively constant, it's very easy to plan. You can use your capacity very closely. On the other hand, if you have a highly peaky seasonal demand signal, you're going to have to do some clever things with inventory planning and capacity management. What's the uncertainty in our forecasts, and how does that affect the global supply network and the input costs? Our team has a saying that all forecasts are wrong, some forecasts are useful. Right? So since all forecasts are wrong, we don't want to build the model at one point that we believe is the forecast. What we really do is build and rebuild many models at many different forecast levels to understand sensitivity. Likewise, we care very much about what does it cost for a network to respond at a certain volume, at a certain response time, given the characteristics of the network. To help people understand that, we create sensitivity charts like this one. So in this case, volume is from low volume to high volume. Time is from very slow response time to very fast response time. The numbers in the cells are incremental profit. So how much profit can I generate with the next unit that I sell? In this chart, blues are good, oranges and browns are bad. So this is, again, a fairly standard product. There's almost always a sweet spot that the network responds really, really well. But when I ask it to increase in volume, I bring online more expensive suppliers. I bring online more expensive plants. I start expediting freight. By the time I get all the way to the right-hand side of the graph, I'm just desperately filling orders, right? I'm running out of capacity. So my total sales may be going up, but my network efficiency is going down, so my profitability is curving off. Likewise, if I have a fixed volume and I try to accelerate the time, once again, I start to run into those hard transportation limits. Eventually, ships only move so fast, trucks only move so fast, pushes inventory into the network. Inventory is not free, reduces profit per unit. Our team likes to say that this corner is what we call no man's land. You want everything and you want it all right now. You can have it, but you probably won't make very much money doing it. These kinds of graphs are the information that we provide to decision makers. So they can look at the volume they're operating at and their current response time to customers. And maybe, if they're here, they can accelerate the response time with only a very small financial penalty. Or maybe if they're here, they would like to change the price to get back here. So understanding the sensitivity of the network in all these different dimensions is really important, and it helps people manage and make good decisions with something that's complex and so big nobody can actually touch it. It's a global system. So if we talk about how should it be transported, we start talking about the transportation modes and lanes, the different kinds of trucks and rail and train and all the different ways that we move Caterpillar products around and its components. Where can we drive volume transportation discounts or take advantage of discounts made by other products? Caterpillar doesn't actually own any trucks. We don't own trains, we don't own rail cars, we don't own ships. We're a commodity buyer. Transportation is purely a commodity. There's a sandwich shop in the United States called Jimmy John's, and they have a sign that says if you were a better customer, you'd buy more sandwiches. That's basically the idea here, is you get better prices if you buy more stuff. So you can buy more stuff in transportation by either buying a big burst contract where you send a lot of volume in one big move, or a long commitment. I commit to sending a constant volume for a long period of time. Ideally, you want both. A lot of volume on one path for a long period of time, but every time you do that, you're making trade-offs with all of the other decisions. So there's a lot of moving parts to that particular piece. What's the trade-off between velocity and cost? Maybe put a little bit simply, do you want the fast, expensive way, or do you want the slow, cheap way? And those two things have implications for inventory because it affects the time to respond to a customer. And how sensitive is the network to energy prices that drive transport costs? So just to give you a little idea about Caterpillar, this is what's called a roll-on, roll-off ship. So this big ramp falls down, and Caterpillar machines are driven onto the ship. So that's typically how we move our bigger machinery. On land, we use these flatbed trucks. And you've probably seen some of them moving around. Actually, had I been thinking, I should have grabbed a Peterlee articulated truck from right here in the UK. This is a graph of energy prices up to about February of this year. So energy price per barrel was way up, north of $100, actually, as recently as 2 years ago, and as low as 39 as recently as a year ago, earlier this year, actually. So the network that we design is highly dependent on the energy price. Why? Well, that bill, when it comes due for Caterpillar, typically in transportation, we spend about $2.5 billion a year moving stuff around. Of that $2.5 billion, $1 billion is directly tied to the price of oil. So when oil prices go up, transport cost goes up, suddenly faraway sources that fill orders at a distance look unattractive because the transport cost goes up. So there's always a balancing act between the cost of energy and the design of the network, along with all the other factors we've talked about so far. So when we talk about minimize environmental impact, we already talked about energy. So now energy is getting converted to carbon, right? So what's the carbon footprint for a particular product model, both its production and its distribution? What's the relationship between our sourcing and transportation decisions and the environment? How do those factors change with demand and response time? So all of those decisions are interlocked together. And one of the ways we visualize this for decision makers is through graphs like this. So in this graph, size of circle is number of machines that a customer wants or dealer wants. Color of circle is the carbon footprint of providing them. So for example, you'll see a dealer in Turkey and a dealer in South Africa have similar numbers of machines that they would like to order. But the carbon footprint to serve South Africa is much higher than what I would serve in Turkey. Well, why is that? Turns out this particular product has a source in Europe. So even though it's the same number of units, the carbon footprint is much higher because I have a much longer supply line. It takes a lot more ships, it takes a lot longer transport. The carbon footprint per unit is much higher. Now sometimes people ask me, why does Caterpillar care? Right? So why do we care about carbon footprint? Well, one is we do have a very serious sustainability goal, and we actually publish our carbon footprint information. So it matters to us in that respect. It matters to our investors too. But the other thing is it sets us up to do strategic analysis, particularly for situations like possibly a future carbon tax. So if you understand how much carbon you're using, you can change the design of your network in response to some future carbon tax scenario. So you really need to know this stuff. If it doesn't happen today, it'll probably happen another day. So now we get to the maximize enterprise profitability, and you might be shocked to learn that Caterpillar is not a charity, right? So we're a for-profit company, we're doing this to make money. So when we consider all of these factors simultaneously, what happens to profitability? Now, in this audience, that may sound like a highly trivial point. Well, of course you would consider them all simultaneously. But believe it or not, the commercial software that companies go out and buy doesn't think that way. Typically, they design a network by saying price at destination minus cost at source minus transport. They lock the structure of the network, so the paths and the connections, and then they tell you need X number of $1 million for inventory. Well, if you're into optimization at all, you realize that that's a sub-optimization. Basically, what you've just done is said, I hope the inventory is not very expensive because I didn't check. Well, that's great if you're Walmart and you're moving socks or tennis shoes or something cheap. If you start adding inventory of $5 million mining machines, people notice. So we want to make sure that we've thought about the inventory implications while we're making all of the other decisions. We really can't separate them. Second piece is which markets and dealers provide the greatest return or the most challenge. We want to understand how that works. And how does the profit walk lay out for different products and sales regions? So this is another typical dashboard, and I'll actually walk you through this in detail in the tools demonstration. Suffice to say for now, size of circle at the top is number of units. Color of circle is profitability. So sometimes I can have two dealers right next to each other with similar number of units but very different profitability. I'll explain why in the demonstration. Ultimately, a lot of what we do in the optimization space comes down to, can you explain it to the accountants? So the accountants are used to thinking in chunk charts, right? So revenue minus product cost, land freight, ocean freight, in-transit inventory, cycle and safety inventory, tariffs, profit. It sounds very intuitive, but you have to remember that there is literally myriad possible combinations of transport and inventory that came into figuring this out. Last piece is over time. Doing it once is hard enough. Maintaining a capability over time is really difficult. So in particular, as we go through a business cycle, how much will profitability change? So you can imagine a business cycle is moving around in the sensitivity table. So I go from low volume to high volume over a different period of time. And my network performs differently at different volumes. Since the future is really uncertain, how do different macroeconomic scenarios apply? For instance, in the United States, as someone pointed out to me just recently, we appear to have elected an internet meme. But as a result, sometimes people wake up and decide they want to build a big, beautiful wall and pull us out of NAFTA. What's that going to do to the whole global network? So it may be a local decision, but it has global implications. So how does this play out? And what are the resilience challenges in this particular network design? So when I talk about resilience, what do I really mean? I'm really talking about the idea of fault tolerance. So if we were speaking in terms of a hardwired network in a building, we'd talk about where's the place where you can really knock the whole system out. In this case, we're talking about very similar things, but instead of not being able to get your web page, we're talking about losing money. So the network, we'd like to know where it's most likely to break and how much profitability is at risk. That might look like this. So dots here, perhaps this line of pink dots is an engine, and this line of pink dots is hydraulic systems, and so on. They flow over an outbound ocean network, a receiving ocean network to our factories, outbound, inbound, customers. And what I'm trying to identify in this complex graph is where's the point of failure that will most impact profitability. If you prefer, think of it as Murphy's Law. Anything that can go wrong will. And it will probably go wrong wherever it does the most damage. Now, part of our Assurance of Supply Center initiative also includes monitoring. So we actually do 24/7 monitoring with what's called geofencing. We know where all of our suppliers are. We know where all of our facilities are. We know where all of the sensitive points are from the network models. We can pick up on an event almost instantly. So for example, a year ago in October, there was a fire in our Gosselies, Belgium facility. Our system found out about the fire in the Gosselies, Belgium plant within 4 minutes. The way it found it out was from a Twitter feed. So I don't know what Twitter is for cat plant on fire in Belgium, but apparently the system does. So it figured that out, and we immediately started modeling what our other alternatives were. So we bring all that together in something we call the Wide Network Library. It's actually a collection of models that cover all the different Caterpillar yellow products. So in this case, from the very smallest over here, our little skid steer product, 226, up to the 6000 series mining shovels that would be larger than this building, and everything in between. Yep. So in this case, we have literally huge numbers of models. So for every single one of these, there's 100 network models at different transport times and volumes and speeds. So what does that look like in terms of resources? There's 14,000 distribution network models in the Wide Network Library. They represent 0.5 terabyte of data. You could think of any individual model as a singular equation that has 100 million variables, every product flowing on every transport line at every moment in time. There's 141 product lines, sorry, 600 million degrees of freedom, my bad. 100 network variations per product line, 100 billion variables in each update. We can solve and resolve that system of equations in 24 hours on Caterpillar's supercomputer. And the mathematics we use to do that work were developed here at Brunel. It takes about 24 clock hours on Cat's supercomputer. We do updates at least 4 times a year and sometimes more. Sometimes more is because certain events drive us to do an update at a time we weren't expecting. So to talk a little bit about that, I'd actually like to do a tools demonstration. So let's actually look at the real tools and how they come together. So to do that, I'm actually going to sit down and drive the machine here for a second. And I'd like to start with just a question to the audience. Where were you on June 23rd last year? Anybody remember? What I truly hope happened on June 23rd is that at least at some point during your day, you went to a polling place. Okay? And the reason we would care about that is because on the morning of June 24th, the world had changed. So the United Kingdom elected to leave the European Union, an event that we colloquially call Brexit. Now that's a little bit confusing because technically you wouldn't really leave the European Union until March 2019, but actually the impact on the global financial system was instantaneous. Now some of those impacts were obvious and some of them were a lot less so. One of the more obvious impacts happened not far away from here. So this is our Leicester facility where we make building construction products. In this case, what we're going to talk about is something called the 901 to 908 compact wheel loader. By Caterpillar standards, it's a little guy, but it's still bigger than your car. What we use this for is building buildings, houses, relatively small construction projects. You could even see them here on campus, possibly. Now, even though the decision made here in the United Kingdom was local, it had global implications. Now, in this particular product's case, that's true because the largest market in the world for that product is not the United Kingdom. It's also not Europe. Actually, the largest market in the world for that product is all the way over here in North America. So prior to Brexit, yellow lines are ocean flow, orange lines are last mile logistics to dealers and customers. The optimal network used a combination of the Leicester facility and another facility in Japan. However, what happened after the vote became public was there was a huge currency shock. So the British pound fell by 5%, almost no change. Fell by 10%, a little bit more change. Fell by 15%, and at this point, essentially, the United Kingdom is on sale. So what we'd really like to do is fill more orders from our source in the United Kingdom. Now there's a lot of questions around that. Can the supply base spin up fast enough to actually take additional load? Do I run out of capacity in my factories? There's a host of other things that have to happen, but a lot of the decision making starts with Gemstone. Do we react? Is it moved far enough for it to matter? How much are we sensitive to? Where do we think it will stop? So the idea is not to build one network model, but to build many network models at many volumes, many currency combinations, and test and test and test all the different possible combinations. It turns out internally to Caterpillar, when this occurred, I made a phone call to one of my peers in the supercomputer center. And I basically told them I need everybody out of the pool. And explained why, and we basically had the whole cluster to ourselves, all 5,000 cores of it. So we were running every possible combination of every product everywhere in the world all the time. Now what's interesting is the whole time people were watching what was happening in the United Kingdom, no one was watching what was happening on the other side of the world. So even if you were reading the news, it barely got any coverage. So all the way on the other side of the world, we have another product. In this case, what's called a 321, 329 excavator. We like to say the big diggy thing with the scoop on the front, right? Very popular product used all over the world. There are 2 factories. One is in Suzhou, China, right here, and the other is in Akashi, Japan. Now, while the pound was falling, the Japanese yen was rising. So typically, the Japanese yen trades in a range about 110 to 130 to the dollar. During the Brexit shock, it hit 99 to the dollar. Well, at 99 to the dollar, all kinds of things happen in the Japanese economy. Keep in mind the Japanese economy is dependent on export. So if your currency is getting stronger, it gets really hard to export and make any money. True for us too. So it turns out we'd like to shift our network from one that looks like this to one that looks like this. So we're going to transfer load from the Japanese plant to the Chinese plant. But you might be asking a question, why didn't we move all of it? I mean, if it's already getting too expensive, why didn't we shift everything? Well, if we follow the yellow lines here at the top to where they're going, we can see that those products are actually going to Mexico. Now, do you remember the comment I made about tariffs earlier? The Japanese have a lower tariff on their products going into Mexico than the Chinese do. Why? Well, Caterpillar didn't cause that to occur. The reason it occurs is because the Japanese automakers have a lot of plants in Mexico. Mexico likes this because it employs a lot of people. So as a result, they give them favorable trade relations. Those favorable trade relations are more important from a profitability standpoint than the change in the currency. So you have to think about the currency implications, the inventory, the energy, all of it, all at the same time simultaneously. So here's the interesting punchline at the end of the day. Within the first 24 hours, we had already recomputed many different combinations of possible currencies and possible volumes, and we communicated to all of the plants that needed to know and product lines that had to take action within the first 24 hours, and the network was already changed. We don't know how long it took our competitors to change, but we know that they at least chased the currency problem for some time. So we're able to do that because of technology that was developed here. Everyone with me so far? Fantastic. What I'd like to do now is change to a different problem, and I'll tell you that this problem is what I would call realistic but not real. And the reason for that is if I want to talk to you about financial calculations and such, I can't use a real product. Aside from the fact that it would be just a silly thing to do in case one of my competitors is in the room, rules in the United States around financial transparency say that I can't do that. But what we're going to look at here is just a little bit about how we look at a typical model. So again, green lines would be from factory to a customer directly over land. Red lines would be factory to an ocean port. Yellow is ocean port to ocean port. Orange is port to a dealer or a customer. The bars are inventory positions. So the inventory is driven there because of my promise to respond to a customer at a certain speed. Now, the reason we use Google Earth, we obviously could communicate all the same data in tables, right, and spreadsheets and things like that, but it doesn't really get decision makers to make a decision. Sometimes we call Excel, data jail. All the data is stuck in the little prison. So the reason we use visualization is not for executainment to keep them entertained, it's because it helps people make better decisions. One of the ways they make better decisions is to understand time. So what we're looking at right now is a snapshot of January. Now, if I grab this, we can see, hang on a sec. I'm going to grab this guy right here and do February, March, April, May, and so on. So demand is constantly changing. There are some customers that buy this product all the time, and there are some customers that come and go. There are some transportation lines that are running all the time, and there's some transportation lines that come and go. Let's play that one more time. So in particular, watch the line flowing to Panama. So there's January, gone in February, back again later, and gone again. So that intermittency makes it difficult to drive a better price. I'm not making a consistent shipment, so I started paying higher prices. But some of those flows are constant. The constant ones are ones that I can leverage to get better prices. Now, if we go over to another region of the world, I can point out the next problem even before I say it. You can probably see it. It looks like a giant grabbed all of those orange transportation or yellow transportation lines. That is the port of Shanghai. So I mentioned earlier that our product moves on roll-on, roll-off freight. Roll-on, roll-off ships require deep water ports. They can't go to just any ocean port. Suppose there was a typhoon that hit something like the port of Shanghai. Where would we go instead? Where's the next available port with available service? Because when I lose that port, all of the customers that are dependent on that set of yellow radial lines are about to lose their product. Turns out the next available location would be down here in Hong Kong. Now that doesn't look all that far. I I mean, here in the UK, that wouldn't be more than a few hours' drive. What you need to know in China is that there is a cottage industry selling noodles to people stuck in trucks for weeks on that little section. So literally, people are sitting in their trucks, going nowhere, and people in little scooters ride out and bring them noodles in order to feed them because they will starve before the commercial product gets to the other end of the system. We need to find these and design better networks. We sometimes use the phrase, don't put all your eggs in one basket. In this case, maybe you don't want to put them all flowing through one port. Maybe you want to diversify. So finding these kinds of issues is really important to the design of our networks. So far, so good? Fantastic. Now, everything we've shown you with this network is at one particular volume or demand forecast and one particular response time. But as I mentioned, we very rarely build models that way. This is the dashboard to describe the results for a range of volume from low to high. Whoops, pardon me. So it'll describe a range of volume from low to high and from very slow to very fast. Now you saw the first one that had a nice curved shape to it. That's a very typically behaving one. When you're trained and you learn how to read these dashboards, very quickly I can see that this network is much more sensitive to volume than it is to response time. That probably means that my factories are close to my customers. So in a competitive situation, I might want to try to promise faster delivery because it's not going to cost me much, and it might cost my competitor quite a bit more. Likewise, I'd like to see how I will leverage different factories. So in this case, Factory 6 is up in Canada, Factory 17 is in Brazil, Factory 32 is in China. The vertical axis is the percentage of available capacity used. So at 2,500 units a year, at its peak, I will use 85% of the Chinese plant's capacity. So what's interesting about that is what happens when the volume increases. So now a user who has access to one of these dashboards, and different teams around the world have access to their dashboards, when I increase the volume to 3,000 units a year, this assumes, of course, all the network actually plays nice when you're doing a live demo. What will happen is this plant will run out of capacity. Now, once it's out of capacity, I have to start filling the orders from somewhere else. The somewhere else turns out to be the Brazil plant. If I go to 3,500 units a year, 4,000, and so on, we've already optimized the network for all different volume levels, all different response times. So we can begin to anticipate where things will grow or where things will change before they change. So it gives us the ability to anticipate the needs of the network before the network has needs. Now at the same time, this is really useful for factory planning, but we're also interested in financial performance of the network. So in this case, what I have color-coded here, this is back to our 2,500 units a year. I'm looking at profitability. I have two plants, or two demands, sorry. In fact, given the resolution in the room, I'm going to zoom that in a little for you. I have one here that needs 14 units, and one here that needs 14 units. But I'm making a profit per unit of 401,000 here, and I'm losing 148,000 here. Well, how did that happen? Well, one of the things I can do is start to look at that with these financial chunk charts. So in this particular case, revenue on sale is 1.3 million, minus our product cost, minus our land freight, ocean freight, in-transit inventory cost here, cycle and safety stock inventory, and those pesky tariffs. Leads to an average profit around the world of this. But if I were to filter this down to what we call EAME, Europe, Africa, Middle East, what I can see is I don't get as high a sales price. My product cost is slightly lower, not a lot different. My tariffs are 109,000 versus a global average of 112. My profit is a little bit lower. So I still need more information. Sometimes I'm losing things in the averaging that's going on. So let's try drilling into the tariffs for a second. So now I've recolored the graph where blue is high, brown is low. At this customer, the tax on each machine is $110,000. But at this customer, the tax is $660,000. So even though they're right next door, that tariff problem drives a huge difference in profitability. And if that was sufficient volume, or if I thought that market was going to grow, I may want to take actions that help me reduce the tariff exposure to my customers. So far, so good. Last step, for this product, we can look at the carbon footprint. So in this case, I can very quickly see at this volume, at this response time, where is most of the carbon going? Most of it's going here. Well, why? Well, in this hypothetical problem, the sources are in Canada, Brazil, and China. There's no good way to get to that location, and they order a lot of machines. So their carbon footprint is going to be relatively high. Is that an issue? It can be, especially if there's a global carbon tax in the future. If that were to be true, then maybe I want to use a different plant to make the products, or maybe I want to change the design of my network in order to minimize that hit. Conversely, maybe I'd rather look at the network from the point of view of the factories. And in this case, since the Chinese factory is the one that's making most of the volume, it's the one incurring most of the carbon, whereas my Canadian plant is so tiny I almost can't see it in this room. And my Brazil plant is right down here. As the network grows, let's go ahead and just double its volume quickly. Now we said, hey, we're going to shift more of that volume to the Brazil plant, so its impact on carbon footprint increases. So far, so good? So the reason we build these kinds of dashboards is because the optimization itself is fairly complex. There's a lot of moving parts, a lot of complexity inside the equations. I'd love to come back and talk about that some other time. But we need to be able to communicate the results to decision makers in ways that they can understand. And they're not going to take the time to sit through 15 different spreadsheets. They really want to understand how the system functions. So that's our goal. What I'm going to do is put us back here and drop us back into the PowerPoint show. Cool. So let's talk a little bit, again, I feel like if I'm in the United Kingdom, I have to say something about Brexit since I'm here, because it seems like the right thing to do, if nothing else, right? But I really want to talk about what's beyond Brexit, or specifically what's beyond the events of last year. So when I think about very complicated systems, I usually like to start off with what I call an influence diagram. Just some simple lines and arrows to help me understand what's happening. So we could think of the Brexit influence diagram as starting off with what the UK does during Brexit and what the EU does during Brexit. And essentially this is hooked up in a feedback loop. So what the UK does will influence what the EU does, and what the EU does will influence what the UK does. So there's kind of a feedback loop here. But there's actually another force that's really important. Those are the things that are happening independent of Brexit. There is a whole lot of things happening in the world outside of the Brexit conversation that I'll submit should probably be part of the conversation. So let's take a look at a few of those as examples, because those are going to influence both sides. One of the scenarios we ran earlier this year is called the hot med scenario. That was driven by a world event. So on the 7th of April, the United States fired 50 Tomahawk missiles into Syria at an area believed to be responsible for a chemical weapons attack on their own citizens. Now, why is that interesting from a global trade perspective? So setting aside the politics, setting aside the military piece for a second, why would global trade care? Why does this matter? Well, it turns out that where it was initiated from is as much or more important than the fact that it happened. Little trivia fact, a Tomahawk missile has a range of about 1,000 nautical miles. That means the US destroyers involved could have destroyed the targets in Syria by firing those missiles from the other side of Spain. But they didn't. Where were the ships? The ships were located immediately south of Crete. Well, why would you do that? Well, from a military standpoint, it minimizes the flight time, so your opponent has less time to react. Also from a military standpoint, the ships happen to be sitting in the only viable flight lane. If the Russians wanted to send aircrafts into Syria, they're not going to go over Turkey because they already got one shot down that direction. They're not going to fly over NATO territory, which means your other option is to fly over 2 active destroyers, which generally will void the warranty, right? But the other piece of it is it was sitting in front of something critically important in global trade. It was sitting in front of the Suez Canal. Now, the Suez Canal has come up different times in history. In fact, people have pursued this path for thousands of years, actually. It actually opened 17th of November 1869, after a lot of others have been working on trying to create a canal for centuries. Even Napoleon tried at one point. The reason it matters is it was expanded on the 24th of February in 2016 for the first time with two-way traffic. So the Suez Canal flows south to north in the morning. It flows north to south in the afternoon and evening. Why is that? Because it's so narrow, ships can't pass each other. So the big project that Egypt undertook just recently was expanding it so at least there's some passing lane. It's a really important thing. 50 ships a day traverse that canal. They carry 2,500 metric tons of cargo per day, linking European markets and Asian markets, two-directional trade. Now that generated $5.3 billion in revenue per year in Egypt in 2015. And they're projecting it'll increase to $13.2 billion in 2023. Well, why are they so confident that the volume of trade is going to go up? Are they counting on growth? Are they counting on functionality? What's going on? I'll submit that what they have is essentially a monopoly. Because all of your other alternatives are atrocious. So if you want to go from, say, somewhere in China or Indonesia or over here-ish to over there-ish, one way you could go would be around the Cape of Good Hope. So all the way down this direction, underneath Africa and up around this side. That will take absolutely forever. It is really, really slow. The other thing we don't usually think about is, yes, it's South Africa, and we think of Africa as being a hot place, but there are icebergs down here. And as we all know, ships and icebergs don't mix. So people don't want to go that direction. You could go through the Strait of Hormuz. So you could come up this direction, run through Iran, cut across Turkey, go into Russia, and come back across the Eastern European states. Not a great route. First problem is going north, the corridor is pretty unfriendly. And when your product finally does get to Europe, it's subject to all kinds of inspections, and people are very, very, very suspicious of anything coming that direction. Conversely, if you put something in the pipeline and try to send it back the other way, there's a good chance it'll never come out the other end. There's things that just get robbed. It happens. What about the Russian rail system? So at this point in history, we can look back and figure out that Soviet-era communism was a giant mistake, but they were really good at civil engineering. So they managed to develop the Trans-Siberian Railway. So we could go this direction. Now the problem with the Russian rail system is that it has very limited transport widths. There's a lot of tunnels that are too narrow even to carry a C-van, let alone a regular rail car. That's the first problem. Second problem is it's really slow because the tracks are really narrow and really old. And third, if you go to the RKD, the Russian state rail service, right there on the front page, they offer armed guard services to make sure your product reaches its destination. Which kind of begs the question, couldn't I just have people not rob me? That would be better, but so it goes. There's actually a fourth option. You could go over the pole. So thanks to climate change, this path is open 4 or 5 months a year, which it never used to be. But nobody goes that way. The first problem, it is fairly quick, but there are really very poor maps. Believe it or not, we've been on this planet for however many years, making maps for however many years, but even the Russians don't have very good maps of this place. What they do know is there are big pointy rocks, and the big pointy rocks are bad, and nobody knows where they are, which means nobody wants to go this direction. The other issue is it's only open part of the year without specialized ships. If you don't make it on your path during time, you will get frozen in, and that's a bad thing. So you either need an ice-breaking hull or you need something else. So one of the reasons the Egyptians can be so confident they're going to make more money is because all of the other options are really horrible. For now, but I'll submit that's about to change. So there's a giant initiative in China called One Belt, One Road. That's actually a fairly poor English translation of the actual project name. One Belt refers to a land link the Chinese government is helping build, combination of roads and rail, running all the way from China, all the way to Europe. The One Road, which is why this is a bad translation, involves sea transport. We normally don't think of roads as sea, but that's okay. So in this case, what they're doing is investing heavily in infrastructure at different port locations in order that container ships can flow more product into Europe. They're spending a lot of money, billions of pounds a year on building this out. Ridiculous amounts of cash. Sometimes they're investing in duplicate infrastructure. For instance, through here, They could use the old Russian rail system, but they don't. They built their own infrastructure. So not only do they want a path that they own. So this is important. It creates a new transportation link from location to location. We've actually sent some prototype product, like just to see how it would work, from here to here. The bad news is, one, it's slow. It's basically as slow as if I'd gone over the ocean route in the first place. Second problem, I can get a faster route, but the faster route that's available costs me so much I would never consider using it. So initially, as it's getting started, it's not terribly attractive. But I would submit that this isn't the only story. So I like to try to cite my sources whenever I'm doing presentations like this. I got this graph from The Economist, but you could find nearly this same graph in about 100 places. And that's because this graph is provided by the Chinese government, and they give it to everybody whenever they decide to talk about One Belt, One Road. But there's another graph that's actually much more interesting. Somebody once said, if you want to know the truth of a thing, follow the money. So in this case, let's follow the yuan. So now what we find out if we follow the yuan, the circles here indicate loans or grants that were made in support of their program. So this is where they've either invested in shipping terminals, they've invested in rail, they've invested in infrastructure. And you can see that happens all along the One Belt and the One Road. So why did they put any money over here? I mean, that doesn't really make any sense, right? I mean, if you're going this direction, what's the point of making any investments on this side? We think we know. So let me show you. If we go back to Google Earth for just a second, I'm going to clear that off and change our position just a little bit to about here. So that is the conventional path. So in this case, this is how I would normally go from Shanghai to Zeebrugge, one of the biggest ports in Europe. But I could have taken this ocean link. Now Mombasa is one of the places where you saw one of those dots, where there's a lot of loan money going in. Thanks to the wonders of satellite technology, these are all brand new high-speed cranes. And that is a ton of port space for handling containers. If we zoom out just a little bit, you'll see a black line. That black line represents a brand new high-speed rail link. That railhead, if you decide to follow it, goes all the way out here to Kampala. Now at that point is where it ends, but it's been built in such a way that it's intended to be extended. If you go over here to Kishkashi, there's an obvious place where they've actually started to put some infrastructure in here, even though it's not connected yet. Follow that over to the other loan location on the other coast. This is Douala. Again, more container port space, but not as built out yet. Black line, brand new rail. So what's really going on is they're getting very close to being able to do this. Create a high-speed rail network from one side of Africa to the other. And if that works, you can then take that path to Zeebrugge, zoom that out, and now you have an alternate network. And the advantage? It doesn't need the Suez Canal. So from a Caterpillar perspective, why would we care? It's all very interesting from a political science perspective, but why would Caterpillar care? Well, the reason we would care is because the current path, about 13,100 miles, takes 42 days in transit. Our best calculations based on the, based on the infrastructure they have, is that that path will be slightly longer, but 28 to 30 days in transit. So they're going to be able to drop that from 42 to 30 days. Now, why does that matter? Well, the faster there's a transportation link, the less the cost of in-transit inventory, the more plausible it becomes to make high-value goods and send them into Europe. So the shorter the transit time, the more attractive it is to high-value goods. So if you were worried about Chinese hot pots and tea things coming over, what you're really going to need to start thinking about is Chinese turbine engines, Chinese high-value equipment flowing into Europe or flowing into the UK. Now that would, on the surface of it, seem to be very bad news. However, I will submit that there's actually something that maybe hasn't been thought all the way through yet. That has to do with the fact that transport networks hate asymmetry. Imagine that you owned a rail company, and your train goes from here to here. You'd actually kind of like to get paid to take the train back, right? So the problem is when you have an asymmetric network, you wind up with really strange pricing. Let's go back to immediately after the Brexit event. By November, so of course that happened in June, by November there was huge asymmetry. So if I took a 40-foot sea van, a typical shipping container, to go from Southampton here in the UK to Savannah, Georgia, cost about $1,700. But to go from Savannah, Georgia back to Southampton cost me $400. How did that happen? Well, again, like we said before, the UK was on sale. There's tons of product flowing into the United States, but now there's a bunch of ships sitting there with nothing to do, and they need to go back and get more stuff. So at $400 a unit, you're basically just covering their fuel bill. So now you have this asymmetry. So I would submit that if they do successfully build this rail network and come up with this particular path, the question is, what could be sent back to Asia? Because if you're going to have asymmetry, now you can send products back along the same pathway, because networks hate asymmetry. So I've been asking during my visit, what is the UK's net exports? So I've been asking a number of different people to try to just sort of guess off the top of their head, what are the net exports of the United Kingdom? And this has been kind of interesting. A lot of people get some of them, but nobody gets all of them, which is kind of cool. So this actually comes from Her Majesty's Revenue and Customs for 2016. So we're looking at net exports. So we're not talking about total exports, we're talking about exports minus imports. What was the net impact of the UK economy? Number one product, antiquities. Sotheby's is doing a great business. They brought in 2.6 billion pounds of stuff and they sold it for 5 billion. It's a pretty good deal when you stop and think about it. Up 2.3 billion positive to the UK economy. What's the number two product? Chemicals, typically industrial chemicals. On top of that is organic chemicals. If you dig into this a little bit farther, you'll find out it's organic chemicals used in biopharmaceuticals. So 6 billion came in, 7 billion went out, netted 1 billion in profit. Scotch. Scotch is a great business. You're up almost $1 billion a year on this stuff. You're quite good at it. Aircraft, spacecraft, parts thereof. So I scribbled all these on my whiteboard at work, and I was sitting there staring at them and going, what on earth do these have in common? And I was struggling and struggling and struggling, but then it finally hit me. They actually do have one extremely important thing in common. It has to do with this idea I would call an economy of trust. You don't buy antiquities from somebody who can't authenticate them. You don't trust your biopharmaceuticals to somebody who doesn't know how to manufacture them. You don't put just any old part on an aircraft or a spacecraft and expect it to work. So these are things that drive net exports in the UK, and they work because the UK has a great reputation for high quality goods with excellent process control. Whether you're talking about validating an antiquity or producing the best whiskey in the world, it's all really about that economy of trust. People trust the UK, and we want to try to preserve that going forward. So as a result, if we go back to our influence diagram, I would submit that the missing link, the thing that really needs to happen during the Brexit negotiations, is how do both parties act and react to the things happening independently of Brexit? Because those forces are huge, and to ignore them would be to ignore both a huge challenge and a massive opportunity. So just to conclude, I'd like to talk a little bit about the future. And strangely, to talk about the future, we always start off by talking about the past. So we've been at the Gemstone program now for a number of years, and we've built a lot of models. Some of those models are really tactical. So this is the short-term kinds of things. How should I route this product to that customer on a Tuesday? All the way on the other end of the spectrum are strategic analysis. How do I respond to Brexit? How do I deal with a new border tax? How do I deal with all the different large macroeconomic forces? Well, what we've learned from lots and lots of models is that tactical products need specificity. I have to build very detailed models with lots of traceability to individual variables, and there's a lot of individual variables. On the other hand, in strategic analysis, sensitivity is key. So how many models can you build, how fast, to try many different possible future world permutations? What we found is that the money is over on the strategic projects. So the high dollar projects are all over here. But over here are the tactical projects, and they get implemented so much faster. So do you want the high dollar projects that take a long time to return, or do you want the fast small dollar projects that you can get a whole lot more quickly? And the short answer is, as team leader, I'm greedy, I want them both. But that causes a technical problem. The technical problem is my high specificity models are massively complex. Put that in perspective, our toy calibration problem for our latest system. If you thought about an edge as a link between any transport lane, any source, any component, any location, the toy problem has 400 quadrillion connections for all the different components, all the different locations, all the different points in time. And that's the toy. The real problems are bigger. On the other end of the spectrum, I have my sensitivity analysis, and it's really about massive model quantity. How quickly can I generate possible permutations? And what I'm looking for are both things that I'm sensitive to, things that I change a lot for, but I'm also looking for, across many scenarios, which things are invariant. Doesn't matter what happens, I'm going to respond the same way as the enterprise. Our work in Gemstone is bounded by these four curves. We can't get involved too soon until the enterprise has done some strategy and market shaping. What customers are we going to serve, what products are we going to offer? Until we know that, we can't design a network. Likewise, it doesn't make a ton of sense to stay involved too late in the system, because we already have investments inside our factories that do the individual buffers and monitoring controls. That's what you pay companies like SAP and other people like that for, is to do that kind of work. We just need to provide them a more intelligent network to do it in, which leads to a focus on the tactical side of things. So if you looked at the way our system works today, and we were to change domains, so let's step out of the supply network space and think about it like a control system. That control system is fundamentally an out-of-the-loop, or what we would call an open-loop control system. That's not necessarily a bad thing. It provides brilliant answers to human questions at the rate people ask the questions to inform their decisions. As a result, we answer the critical questions as events unfold, and we improve decision quality. This is a good thing, but it's not a sufficient thing. We think the next stage is something we call entering the loop. And in that case, it's really about context sensitivity. Some questions, some events are eminently anticipatable. For example, I know that energy prices are going to trade between a range of A and B. In which case, why do I wait to see what the energy price is in the morning when I could have just rebuilt all of the models at many different energy prices and already know the answer for where I'm sensitive? So I should stop waiting to be asked. I should start using the tools ahead of the need to understand what I'm sensitive to before it happens. Because when I do that, I can find action triggers that let me position resources ahead of time. Next one is on the loop stage. Here we're seeking informed consent of a human at the rate people evaluate and approve the actions that are presented. When I describe this to people, sometimes I think of it like in the Cold War. Remember the old big red button? You had the plastic lid you flipped up and then you push the button. We want to get as far as making the button with the plastic lid, but we won't push it. In this case, it's still up to the humans to decide if they agree. There's always a degree of human control. Now that'll be good because we'll be able to link what we know in the network to what we do in the network and allow us to accelerate response. So instead of saying, oh, this is what the model says, I guess I should do X, I'll start marshaling the resources to do X. Instead, we will have already marshaled the resources to do X and say, are you ready to go, or do you want to change the plan? Which leads to the last stage, the in-the-loop control. Now, if we're going to go to full closed-loop, in-the-loop control, we have to be able to explain our actions ahead of the time they're taken. The reason for that is the humans aren't going to let us do this unless they understand. And I'm also worried about, as an engineer, the rate at which information is obtained and validated. What I don't want to do is essentially hand an artificially intelligent system the corporate Visa card and have it run off in some direction because it got a bad piece of data. All right? It would be catastrophic. So I have to have the ability to know whether the data is reasonable, whether it's intelligent, whether it's actionable, or whether it's probably something I really need to find a human and ask a question to. But if we do it, we'll be able to intelligently plan and execute the network in real time and adapt to a dynamic marketplace before things occur. It's an ambitious idea. It's a little bit of a crazy idea, but they told us we were crazy 7 years ago too. So I think a lot of this gets summarized down to a really simple, elegant Japanese proverb. Vision without action is a daydream, and action without vision is a nightmare. What we've been able to do at Brunel is put vision and action together to create a system that changes Caterpillar and changes the world. That gives me some confidence that we can probably do the next thing too. Well, I hope you enjoyed the presentation. This is kind of the complete material that I had for today, and I'd be more than happy to field questions. Thank you.